Our first learning algorithm will be linear regression. In this video, you see what the model looks like, and more importantly, you also see what the overall process of supervised learning looks like. Let's use our motivating example of predicting housing prices. We're going to use a data set of housing prices from the city of Portland, Oregon, and here I'm going to plot my data set of a number of houses that were of different sizes that were sold for a range of different prices. Let's say that given this data set, you have a friend that's trying to sell a house, and let's say your friend's house is of size 1,250 square feet, and you want to tell them how much they might be able to sell the house for. Well, one thing you could do is fit a model, maybe fit a straight line to this data. That might look something like that. And based on that, maybe you could tell your friend that looks like they can maybe sell the house for around $220,000. So this is an example of a supervised learning algorithm, and it's supervised learning because we're given the quote right answer for each of our examples. Namely, we're told what was the actual house, what was the actual price that each of the houses in our data set was sold for. And moreover, this is an example of a regression problem where the term regression refers to the fact that we're predicting a real value output, namely the price. And just to remind you, the other most common type of supervised learning problem is called a classification problem, where we predict discrete values outputs, such as if we are looking at cancer tumors and trying to decide if a tumor is malignant or benign. So there's a 0-1 value discrete output. More formally, in supervised learning, we have a data set, and this data set is called a training set. So for a housing price example, we have a training set of different housing prices, and our job is to learn from this data how to predict the prices of the houses. Let's define some notation that we're using throughout this course. I'm going to define quite a lot of symbols. It's okay if you don't remember all the symbols right now, but as the course progresses, it'll be useful to have a convenient notation. So I'm going to use lowercase m throughout this course to denote the number of training examples. So in this data set, if I have, let's say 47 rows in this table, then I have 47 training examples, and m equals 47. I'm going to use lowercase x to denote the input variables, often also called the features. So that'll be x's here, would be our input features. And I'm going to use y to denote my output variables, or the target variable which I'm trying to predict. And so that's this second column here. A little bit more notation. I'm going to use x comma y to denote a single training example. So a single row in this table corresponds to a single training example. And to refer to a specific training example, I'm going to use this notation xi comma yi, and going to use this to refer to the ith training example. Right? So this superscript I over here, this is not exponentiation, right? This xiyi, the superscript I in parentheses, that's just an index into my training set, and it refers to the ith row in this table. Okay, so this is not x to the power of I, y to the power of I. Instead, xiyi just refers to the ith row of this table. So, for example, x1, refers to the input value from the first training example. So that's 2104, right? Because that's x in the first row. x2 will be equal to 1416, right? That's the second x, and y1 will be equal to 460, because that's the y value for my first training example. That's what that 1 refers to. So as mentioned, occasionally I'll ask you a question to let you check your own understanding. In a few seconds in this video, a multiple choice question will pop up in the video. When it does, please use your mouse to select what you think is the right answer. We've defined what a training set is, and so here's how a supervised learning algorithm works. We started with a training set, like our training set of housing prices, and we feed that to our learning algorithm. It's the job of a learning algorithm to then output a function which by convention is usually denoted lowercase h, and h stands for hypothesis. And what the job of the hypothesis is a function that takes as input the size of a house, like maybe the size of a new house that your friend is trying to sell, so it takes in a new value of x, and it tries to output the estimated value of y for the corresponding house. So h is a function that maps from x's to y's. People often ask me, why is this function called a hypothesis? Some of you may know the meaning of the term hypothesis from the dictionary or from science or whatever. It turns out that in machine learning, this is a name that was used in the early days of machine learning, and it kind of stuck. It's maybe not a great name for this sort of function for mapping from sizes of houses to the predictions, but I think the term hypothesis maybe isn't the best possible name for this, but it's the standard terminology that people use in machine learning now. So don't worry too much about why people call it that. When designing a learning algorithm, the next thing we need to decide is how do we represent this hypothesis h? For this and the next few videos, I'm going to choose our initial choice for representing the hypothesis will be the following. I'm going to represent h as follows. I'm going to write to this h subscript theta of x equals theta 0 plus theta 1 of x. And as a shorthand, sometimes instead of writing h subscript theta of x, sometimes as a shorthand I'll just write this as h of x, but more often I'll write it as a subscript theta over there. And plotting this in pictures, all this means is that we are going to predict that y is a linear function of x. Right? So that's our data set. And what this function is doing is it's predicting that y is some straight line function of x. That's h of x equals theta 0 plus theta 1 x. Okay? And why a linear function? Well, sometimes we'll want to fit more complicated, perhaps nonlinear functions as well. But since this linear case is the simpler building block, we'll start with this example first of fitting linear functions, and we'll build on this to eventually have more complex models and more complex learning algorithms. Let me also give this particular model a name. This model is called linear regression, or this particular example is actually linear regression with one variable, with the variable being x. Right? So predicting housing prices is a function of the one variable x. And another name for this model is univariate linear regression. And univariate is just a fancy way of saying one variable. So that's linear regression. In the next video, we'll start to talk about just how to go about implementing this model. In this video, we'll define something called the cost function. This will let us figure out how to fit the best possible straight line to our data. In linear regression, we have a training set like that shown here. Remember our notation, m was the number of training examples, so maybe m equals 47. And the form of our hypothesis, which we use to make predictions, is this linear function. To introduce a little bit more terminology, these theta 0 and theta 1, right, these theta i's are what are called the parameters of the model. And what we're going to do in this video is talk about how to go about choosing these two parameter values, theta 0 and theta 1. With different choices of the parameters theta 0 and theta 1, we get different hypotheses, different hypothesis functions. I know some of you will probably be already familiar with what I'm going to do on this slide, but just to review, here are a few examples. If theta 0 is 1.5 and theta 1 is 0, then the hypothesis function will look like this. Right? Because your hypothesis function will be h of x equals 1.5 plus 0 times x, which is this constant value function that's just flat at 1.5. If theta 0 equals 0, theta 1 equals 0.5, then the hypothesis will look like this. And it should pass through this point 2, 1, since you now have h of x, so really h substrate theta of x, but sometimes I'll just omit theta for brevity. So h of x will be equal to just 0.5 times x, which looks like that. And finally, if theta 0 equals 1 and theta 1 equals 0.5, then we end up with a hypothesis that looks like this. Let's see, I should pass through the 2 point like so, and this is my new h of x, or my new h subscript theta of x. All right, well, you remember I said that this is h subscript theta of x, but as a shorthand, sometimes I'll just write this as h of x. In linear regression, we have a training set, like maybe the one I've plotted here. What we want to do is come up with values for the parameters theta 0 and theta 1, so that the straight line we get all of this corresponds to a straight line that somehow fits the data well, like maybe that line out there. So how do we come up with values theta 0, theta 1 that corresponds to a good fit to the data? The idea is we're going to choose our parameters theta 0, theta 1 so that h of x, meaning the value we predict on inputs x, that this is at least close to the values y for the examples in our training set, for our training examples. So in our training set, we're given a number of examples where we know x, the size of the house, and we know the actual price it was sold for. So let's try to choose values for the parameters so that at least in the training set, given the x's in the training set, we make reasonably accurate predictions for the y values. Let's formalize this. So in linear regression, what we're going to do is I'm going to want to solve a minimization problem. So I'm going to write minimize over theta 0, theta 1. And I want this to be small, right? I want the difference between h of x and y to be small. And one thing I might do is try to minimize the squared difference between the output of my hypothesis and the actual price of a house. Okay? So let's fill in some details. You remember that I was using the notation xi comma yi to represent the ith training example. So what I want really is to sum over my training set, sum from I equals 1 to m, of the squared difference between, this is the prediction of my hypothesis when it is input the size of house number I, right, minus the actual price that house number I was sold for. And I want to minimize a sum over my training set, sum from I equals 1 through m, of the difference, of the squared error, squared difference between the predicted price of a house and the price that it was actually sold for. And just to remind you of your notation, m here was the size of my training set, right? So the m there is my number of training examples. Right? That hash sign is the abbreviation for number of training examples. Okay? And to make some of our later math a little bit easier, I'm going to actually look at 1 over m times that. So we're going to try to minimize my average error, which is going to minimize 1 over 2m. Putting the 2, the constant 1/2 in front, it just makes some of the math a little bit easier. So minimizing 1/2 of something, right, should give you the same values for the parameters theta 0 and theta 1 as minimizing that function. And just to make sure this equation is clear, right? This expression in here, h subscript theta of x, this is our usual, right? That's equal to this plus theta 1 xi. And this notation, minimize over theta 0 and theta 1, this means find me the values of theta 0 and theta 1 that causes this expression to be minimized. And this expression depends on theta 0 and theta 1. Okay? So just to recap, we're posing this problem as, find me the values of theta 0 and theta 1 so that the average, or really 1 over 2m times the sum of squared errors between my predictions on the training set minus the actual values of the houses on the training set is minimized. So this is going to be my overall objective function for linear regression. And just to rewrite this out a little bit more cleanly, what I'm going to do is, by convention, we usually define a cost function, which is going to be exactly this, that formula that I have up here. And what I want to do is minimize over theta 0 and theta 1 my function j of theta 0, comma, theta 1, where just write this out. This is my cost function. So this cost function is also called the squared error function, or sometimes called the squared error cost function. And it turns out that why do we take the squares of the errors? It turns out that the squared error cost function is a reasonable choice and will work well for most problems, for most regression problems. There are other cost functions that will work pretty well, but the squared error cost function is probably the most commonly used one for regression problems. Later in this class we'll talk about alternative cost functions as well, but this choice that we just had should be a pretty reasonable thing to try for most linear regression problems. Okay, so that's the cost function. So far we've just seen a mathematical definition of this cost function, and in case this function j of theta 0, theta 1, in case this function seems a little bit abstract and you still don't have a good sense of what it's doing, in the next video, in the next couple of videos, I'm actually going to go a little bit deeper into what the cost function j is doing and try to give you better intuition about what it's computing and why we want to use it. In the previous video, we gave a mathematical definition of the cost function. In this video, let's look at some examples to get better intuition about what the cost function is doing and why we want to use it. To recap, here's what we had last time. We want to fit a straight line to our data, so we had this form as a hypothesis with these parameters theta 0 and theta 1, and with different choices of the parameters, we end up with different straight line fits to the data, h of x like so. And there's a cost function, and that was our optimization objective. For this video, in order to better visualize the cost function j, I'm going to work with a simplified hypothesis function, like that shown on the right. So I'm going to use a simplified hypothesis, which is just theta 1 times x. You can, if you want, think of this as setting the parameter theta 0 equal to 0. So I have only one parameter, theta 1, and my cost function is similar to before, except that now h of x, that is now equal to just theta 1 times x. And I have only one parameter, theta 1, and so my optimization objective is to minimize j of theta 1. In pictures, what this means is that if theta 0 equals 0, that corresponds to choosing only hypothesis functions that pass through the origin, that pass through the point 0, 0 over there. Using the simplified definition of a hypothesis and cost function, let's try to understand the cost function concept better. It turns out there are two key functions we want to understand. The first is the hypothesis function, and the second is the cost function. So notice that the hypothesis, right, h of x, for a fixed value of theta 1, this is a function of x. So the hypothesis is a function of what is the size of the house x. In contrast, the cost function, j, that's a function of the parameter theta 1, which controls the slope of your straight line. Let's plot these functions and try to understand them both better. Let's start with the hypothesis. On the left, let's say here's my training set with 3 points at 1, 1, 2, 2, and 3, 3. Let's pick a value of theta 1. So I'm going to set theta 1 equals 1, and if that's my choice for theta 1, then my hypothesis is going to look like this straight line over here. Okay? And I want to point out, when I'm plotting my hypothesis function, my x-axis, my horizontal axis is labeled x, is labeled, size of the house over here. Now, I've temporarily set theta 1 equals 1. What I want to do is figure out, what is j of theta 1 when theta 1 equals 1. So let's go ahead and compute what the cost function is for the value 1. Well, as usual, my cost function is defined as follows, right? Sum over my training set of this usual squared error term. And this is therefore equal to this of theta 1 xi minus yi. And if you simplify, this turns out to be that 0 squared plus 0 squared plus 0 squared, which is of course just equal to 0. Now, inside the cost function, it turns out each of these terms here is equal to 0 because, for the specific training set I have, where my 3 training examples are at 1, 1, 2, 2, 3, 3, if theta 1 is equal to 1, then, h of x, right, h of xi is equal to yi exactly. Let me write this better. Right? And so h of x minus y, each of these terms is equal to 0, which is why I find that j of 1 is equal to 0. So we now know that j of 1 is equal to 0. Let's plot that. What I'm going to do on the right is plot my cost function j. And notice, because my cost function is a function of my parameter theta 1, when I plot my cost function, the horizontal axis is now labeled with theta 1. So I have j of 1 is equal to 0. So let's go ahead and plot that. You can end up with an x over there. Now let's look at some other examples. Theta 1 can take on a range of different values, right? So theta 1 can take on negative values, 0, or positive values. So what if theta 1 is equal to 0.5? What happens then? Let's go ahead and plot that. I'm now going to set theta 1 equals 0.5, and in that case, my hypothesis now looks like this. There's a line with slope equals to 0.5, and let's compute j of 0.5. So that is going to be 1 over 2m of my usual cost function. It turns out that the cost function is going to be the sum of squared values of the height of this line plus the sum of squared of the height of that line plus the sum of squared of the height of that line, right? Because this vertical distance, that's the difference between, y, I, and the predicted value h of xi, right? So the first example, this is going to be 0.5 minus 1 squared, because my hypothesis predicted 0.5, whereas the actual value was 1. For my second example, I get 1 minus 2 squared, because my hypothesis predicted 1, but the actual housing price was 2. And then finally, plus 1.5 minus 3 squared. And so that's equal to 1 over 2 times 3, because m, my training set size, right, I have 3 training examples. And then that's times, simplifying the thing in parentheses, is 3.5. So that's 3.5 over 6, which is about 0.68. So now we know that j of 0.5 is about 0.68. Let's go and plot that. Oh, excuse me, math error. This is actually 0.58. So I'm going to plot that, which is maybe about over there. Okay. Now, let's do one more. How about if theta 1 is equal to 0? What is j of 0 equal to? It turns out that if theta 1 is equal to 0, then h of x is just equal to, this flat line, right? That just goes horizontally like this. And so measuring the errors, we have that j of 0 is equal to 1 over 2m times 1 squared plus 2 squared plus 3 squared, which is 1/6 times 14, which is about 2.3. So let's go ahead and plot that as well. We end up with a value around 2.3. And of course, we can keep on doing this for other values of theta 1. It turns out that you can have negative values of theta 1 as well. So if theta 1 is negative, then h of x would be equal to, say, minus 0.5 times x, right? If theta 1 is minus 0.5. And so that corresponds to a hypothesis, with a slope of negative 0.5. And you can actually keep on computing these errors. This turns out to be, for 0.5, it turns out to be a really high error. It works out to be something like 5.25 and so on. And for different values of theta 1, you can compute these things, right? And it turns out that you compute a range of values, you get something like that. And by computing the range of values, you can actually slowly trace out what this function j of theta looks like. And that's what j of theta is. To recap, for each value of theta 1, right, each value of theta 1 corresponds to a different hypothesis or to a different straight line fit on the left. And for each value of theta 1, we could then derive a different value of j of theta 1. And for example, theta 1 equals 1 corresponded to this straight line fit through the data, whereas theta 1 equals 0.5, this point, shown in magenta, corresponded to maybe that line, and theta 1 equals 0, which I'm going to show in blue, that corresponds to this horizontal line, right? So for each value of theta 1, we wound up with a different value of j of theta 1, and we could then use this to trace out this plot on the right. Now, remember, the optimization objective for our learning algorithm is we want to choose the value of theta 1 that minimizes j of theta 1, right? This was our objective function for linear regression. Well, looking at this curve, the value that minimizes j of theta 1 is, theta 1 equals to 1. And lo and behold, that is indeed the best possible straight line fit through our data. By setting theta 1 equals 1, for this particular training set, we actually end up fitting it perfectly. And that's why minimizing j of theta 1 corresponds to finding a straight line that fits the data well. So, to wrap up, in this video, we looked at some plots to understand the cost function. To do so, we simplified the algorithm so that it had only one parameter theta 1, and we set the parameters theta 0 to equal to 0. In the next video, we'll go back to the original problem formulation and look at some visualizations involving both theta 0 and theta 1, that is, without setting theta 0 to 0. And hopefully that will give you an even better sense of what the cost function j is doing in the original linear regression formulation. In this video, let's delve deeper and get even better intuition about what the cost function is doing. This video assumes that you're familiar with contour plots. If you're not familiar with contour plots or contour figures, some of the illustrations in this video may or may not make sense to you, but it's okay, and if you end up skipping this video or if some of it doesn't quite make sense because you haven't seen contour plots before, that's okay, and you still understand the rest of this course without those parts of this. Here's our problem formulation as usual with the hypothesis, parameters, cost function, and our optimization objective. Unlike before, unlike the last video, I'm going to keep both of my parameters theta 0 and theta 1 as we generate our visualizations for the cost function. So, same as last time, we want to understand the hypothesis, h, and the cost function j. So here's my training set of housing prices. And let's pick some hypothesis, like that one. This is not a particularly good hypothesis, but if I set theta 0 equals 50 and theta 1 equals 0.06, then I end up with this hypothesis down here, and that corresponds to that straight line. Now, given these values of theta 0 and theta 1, we want to plot the corresponding, cost function on the right. What we did last time was, when we only had theta 1, we were drawing plots that look like this as a function of theta 1. But now we have two parameters, theta 0 and theta 1, and so the plot gets a little more complicated. It turns out that when we had only one parameter, the plots we drew had this sort of bow-shaped function. Now, when we have two parameters, it turns out the cost function also has a similar sort of bow shape. And in fact, depending on your training set, you might get a cost function that maybe looks something like this. So this is a 3D surface plot where the axes are labeled theta 0 and theta 1. So as you vary theta 0 and theta 1, the two parameters, you get different values of the cost function j of theta 0 comma theta 1. And the height of this surface above a particular point of theta 0, theta 1, right, that's the vertical axis, the height of the surface at the point indicates the value of j of theta 0, comma, j of theta 1. And you can see it sort of has this bow-like shape. Let me show you the same plot in 3D. So here's the same figure in 3D with axes theta 0, theta 1, and vertical axis j of theta 0, theta 1. And if I rotate this plot around, you kind of get a sense, I hope, of this sort of bow-shaped surface. That's what the cost function j looks like. Now, for the purpose of illustration, in the rest of this video, I'm not actually going to use these sorts of 3D surfaces to show you the cost function j. Instead, I'm going to use contour plots, or what I also call contour figures. I guess they mean the same thing. To show you these surfaces. So here's an example of a contour figure shown on the right, where the axes are theta 0 and theta 1. And what each of these ovals, what each of these ellipses shows is a set of points that takes on the same value for j of theta 0, theta 1. So concretely, for example, let's take that point and that point and that point. All three of these points that I just drew in magenta, they have the same value for j of theta 0, theta 1. Okay, this is a theta 0, theta 1 axis, but those three have the same value for j of theta 0, comma, theta 1. And if you haven't seen contour plots much before, imagine, if you will, a bow-shaped function that's coming out of my screen, so that the minimum, so the bottom of the bow is this point right there, right, the middle of these concentric ellipses. And imagine a bow shape that sort of grows out of my screen like this, so that each of these ellipses has the same height above my screen, and the minimum of the bow, right, is right down there. And so the contour figures is a way to, maybe a more convenient way to visualize my function j. So let's look at some examples. Over here, I have a particular point, right? And so this is with, theta 0 equals maybe about 800, and theta 1 equals maybe a minus 0.15. And so this point, right, this point in red corresponds to one particular pair of values of theta 0, comma, theta 1. And they correspond, in fact, to that hypothesis, right? With theta 0, it's about 800, so this intersects the vertical axis around 800, and this is a slope of about minus 0.15. Now, this line is really not such a good fit to the data, right? This hypothesis, h of x, with these values of theta 0, theta 1, it's really not such a good fit to the data, and so you find that its cost is a value that's out here, that's pretty far from the minimum. Right, so it's pretty far, this is a pretty high cost because this is just not that good a fit to the data. Let's look at some more examples. Now here's a different hypothesis that's, still not a great fit to the data, but maybe slightly better. So here, right, that's my point, those are my parameters, theta 0, theta 1. And so my theta 0 value, right, that's about 360. And my value for theta 1 is equal to 0. So, let's write that out. This theta 0 equals 360, theta 1 equals 0. And this pair of parameters corresponds to that hypothesis, corresponds to a flat line, right? This is h of x equals 360 plus 0 times x. So that's my hypothesis. And this hypothesis, again, has some cost, and that cost is, plotted as the height of the j function at that point. Let's look at just a couple of examples. Here's one more. At this value of theta 0 and at that value of theta 1, we end up with this hypothesis h of x. And again, not a great fit to the data, and we just actually move even further out for the minimum. Last example. This is actually not quite at the minimum, but it's pretty close to the minimum. So this is not such a bad fit to the data, where for a particular value of theta 0, which whatever this value is, and for a particular value of theta 1, we get a particular h of x. And this is not quite at the minimum, but it's pretty close. And so the sum of squares errors, the sum of squares distances between my training examples and my hypothesis. So really, that's the sum of squared distances, right, of all of these errors. This is pretty close to the minimum, even though it's not quite the minimum. So with these figures, I hope that gives you a better understanding of what values of the cost function j and how they are, and how that corresponds to different hypotheses, as well as how better hypotheses may correspond to points that are closer to the minimum of this cost function j. Now, of course, what we really want is an efficient algorithm, like an efficient piece of software for automatically finding the value of theta 0 and theta 1 that minimizes the cost function j. Right? And what we don't want to do is to have to write software to plot out this point and then try to manually read off the numbers. That's just not a good way to do it. And in fact, we'll see later that when we look at more complicated examples, we'll have higher dimensional figures with more parameters. That it turns out we'll see later in this course examples where this figure cannot really be plotted and it becomes much harder to visualize. And so what we want is to have software to find the value of theta 0, theta 1 that minimizes this function. And in the next video, we'll start to talk about an algorithm for automatically finding that value of theta 0 and theta 1 that minimizes the cost function j. We previously defined the cost function j. In this video, I want to tell you about an algorithm called gradient descent for minimizing the cost function j. It turns out gradient descent is a more general algorithm and is used not only in linear regression, it's actually used all over the place in machine learning. And later in the class, we'll use gradient descent to minimize other functions as well, not just the cost function j for linear regression. So in this video, we're going to talk about gradient descent for minimizing some arbitrary function j, and then in later videos, we'll take this algorithm and apply it specifically to the cost function j that we had defined for linear regression. So here's the problem setup. Going to assume that we have some function j of theta 0, comma theta 1. Maybe it's a cost function from linear regression. Maybe it's some other function we want to minimize. And we want to come up with an algorithm for minimizing that as a function of j of theta 0, theta 1. Just as an aside, it turns out that gradient descent actually applies to more general functions. So imagine if you have a function that's a function of j of theta 0, theta 1, theta 2, up to, say, some theta n, and you want to minimize theta 0, you minimize over theta 0 up to theta n of this j of theta 0 up to theta n. It turns out gradient descent is an algorithm for solving sort of this more general problem, but for the sake of brevity, for the sake of succinctness of notation, I'm just going to pretend I have only 2 parameters throughout the rest of this video. Here's the idea for gradient descent. What we're going to do is we're going to start off with some initial guesses for theta 0 and theta 1. Doesn't really matter what they are, but a common choice would be if we set theta 0 to 0 and set theta 1 to 0. Just initialize them to 0. What we're going to do in gradient descent is we'll keep changing theta 0 and theta 1 a little bit to try to reduce j of theta 0, theta 1 until hopefully we wind up at a minimum, or maybe at a local minimum. So let's see in pictures what gradient descent does. Let's say you're trying to minimize this function. So notice the axes. This is theta 0, theta 1 on the horizontal axis, and j is the vertical axis. And so the height of the surface shows j, and we want to minimize this function. So we're going to start off with theta 0, theta 1 at some point. So imagine picking some value for theta 0, theta 1, and that corresponds to starting at some point on the surface of this function. Okay, so whatever value of theta 0, theta 1 gives you some point here. I didn't initialize them to 0, 0, but sometimes you initialize it to other values as well. Now, I want you to imagine that this figure shows a hill. Imagine this is like the landscape of some grassy park with 2 hills like so. And I want you to imagine that you are physically standing at that point on the hill, right, on this little red hill in your park. In gradient descent, what we're going to do is we're going to spin 360 degrees around, just look all around us and ask, if I were to take a little baby step in some direction, and I want to go downhill as quickly as possible, what direction do I take that little baby step in if I want to go down, if I sort of want to physically walk down this hill as rapidly as possible? Turns out that if you're standing at that point on the hill, you look all around, you find that the best direction to take a little step downhill is roughly that direction. Okay? And now you're at this new point on your hill. You're going to again look all around and then say, what direction should I step in order to take a little baby step downhill? And if you do that and take another step, you take a step in that direction. And then you keep going. You know, from this new point, you look around, decide what direction will take you downhill most quickly, take another step, and so on, until you converge to this local minimum down here. Gradient descent has an interesting property. This first time we ran gradient descent, we were starting at this point over here, right? Started at that point over here. Now imagine we had initialized gradient descent just a couple steps to the right. Imagine we initialized gradient descent with that point on the upper right. If you were to repeat this process, so start from that point, look all around, take a little step in the direction of steepest descent, you would do that, then look around, take another step, and so on. And if you started just a couple steps to the right, gradient descent would have taken you to this second local optimum over on the right. So if you had started at this first point, you would have wound up at this local optima. But if you started just a little bit, in a slightly different location, you would have wound up at a very different local optimum. And this is a property of gradient descent that we'll say a little bit more about later. So that's the intuition in pictures. Let's look at the math. This is the definition of the gradient descent algorithm. We're going to just repeatedly do this until convergence. We're going to update my parameter theta j by taking theta j and subtracting from it alpha times this term over here. Okay, so let's see. There are a lot of details in this equation, so let me unpack some of it. First, this notation here, colon equals, I'm going to use colon equals to denote assignment. So the assignment operator. So concretely, if I write a colon equals b, what this means is it means, in a computer, this means take the value in b and use it to overwrite whatever value is a. So this means, set a to be equal to the value of b. Okay, so it's assignment. And I can also do a colon equals a plus 1. This means take a and increase its value by 1. Whereas in contrast, if I use the equal sign, if I write a equals b, then this is a truth assertion. Okay, so if I write a equals b, then I'm asserting that the value of a equals to the value of b. Right? So the left-hand side, that's a computer operation where you set the value of a to a new value. The right-hand side, this is asserting, I'm just making a claim that the values of a and b are the same. And so whereas I can write a colon equals a plus 1, that means increment a by 1. Hopefully, I won't ever write a equals a plus 1 because that's just wrong, right? A and a plus 1 can never be equal to the same values. Okay, so that's the first part of the definition. This alpha here is a number that is called the learning rate. And what alpha does is it basically controls how big a step we take downhill with gradient descent. So if alpha is very large, then that corresponds to a very aggressive gradient descent procedure where we're trying to take huge steps downhill. And if alpha is very small, then we're taking little baby steps downhill. And I'll come back and say more about this later, about how to set alpha and so on. And finally, this term here, that's a derivative term. I don't want to talk about it right now, but I will derive this derivative term and tell you exactly what this is later. Okay, and some of you will be more familiar with calculus than others, but even if you aren't familiar with calculus, don't worry about it. I'll tell you what you need to know about this term here. Now, there's one more subtlety about gradient descent, which is in gradient descent, we're going to update, theta 0 and theta 1, right? So this update takes place for j equals 0 and j equals 1. So you're going to update theta 0 and update theta 1. And the subtlety of how you implement gradient descent is for this expression, right, for this update equation, you want to simultaneously update theta 0 and theta 1. What I mean by that is that, in this equation, we're going to update theta 0 equals theta 0 minus something, and update theta 1 equals theta 1 minus something. And the way to implement this is you should compute the right-hand side, right? Compute that thing for theta 0 and theta 1, and then simultaneously, at the same time, update theta 0 and theta 1. Okay? So let me say what I mean by that. This is a correct implementation of gradient descent, meaning a simultaneous update. So I'm going to set temp 0 equals that, set temp 1 equals that, so basically compute the right-hand sides. And then having computed the right-hand sides and stored them in two variables, temp 0 and temp 1, I'm going to update theta 0 and theta 1 simultaneously. So that's the correct implementation. In contrast, here's an incorrect implementation that does not do a simultaneous update. So in this incorrect implementation, we compute temp 0, and then we update theta 0, and then we compute temp 1, and then we update temp 1. And the difference between the right-hand side and the left-hand side implementations is that if you look down here, if you look at this step, if by this time you've already updated theta 0, then you would be using the new value of theta 0 to compute this derivative term. And so this gives you a different value of temp 1 than the left-hand side, right? Because you've now plugged in the new value of theta 0 into this equation. And so this on the right-hand side is not a correct implementation of gradient descent. Okay? So I don't want to say why you need to do the simultaneous updates. It turns out that, the way gradient descent is usually implemented, which we'll say more about later, it actually turns out to be more natural to implement the simultaneous update. And when people talk about gradient descent, they always mean simultaneous update. If you implement the non-simultaneous update, it turns out it will probably work anyway, but this algorithm on the right is not what people refer to as gradient descent, and this is some other algorithm with different properties. And for various reasons, this can behave in slightly stranger ways. And so, what you should do is really implement the simultaneous update of gradient descent. So that's the outline of the gradient descent algorithm. In the next video, we're going to go into the details of the derivative term, which I wrote out but didn't really define. And if you've taken a calculus class before, and if you're familiar with partial derivatives and derivatives, it turns out that's exactly what that derivative term is. But in case you aren't familiar with calculus, don't worry about it. The next video will give you all the intuitions and will tell you everything you need to know to compute that derivative term, even if you haven't seen calculus or even if you haven't seen partial derivatives before. With the next video, hopefully we'll be able to give you all the intuitions you need to apply gradient descent. In the previous video, we gave a mathematical definition of gradient descent. Let's delve deeper and in this video get better intuition about what the algorithm is doing and why the steps of the gradient descent algorithm might make sense. Here's the gradient descent algorithm that we saw last time. And just to remind you, this parameter or this term alpha is called the learning rate, and it controls how big a step we take when updating my parameter theta j. And this second term here is the derivative term. And what I want to do in this video is give you better intuition about what each of these two terms is doing and why, when put together, this entire update makes sense. In order to convey these intuitions, what I want to do is use a slightly simpler example where we want to minimize a function of just one parameter. So we have, say we have a cost function j of just one parameter, theta 1, like we did a few videos back, where theta 1 is a real number. Okay, so just again, so we can have 1D plots, which are a little bit simpler to look at. And let's try to understand what gradient descent will do on this function. So let's say here's my function j of theta 1. And so that's my, and where theta 1 is a real number. Right? Now, let's say I've initialized gradient descent with theta 1 at this location. So imagine that we start off at that point on my function. What gradient descent will do is it will update theta 1 gets updated as theta 1 minus alpha times dd theta 1 j of theta 1, right? And as an aside, this derivative term, right? If you're wondering why I changed the notation from these partial derivative symbols, if you don't know what the difference is between these partial derivative symbols and the dd theta, don't worry about it. Technically, in mathematics, we call this a partial derivative, we call this a derivative, depending on the number of parameters in the function j. But that's a mathematical technicality. So, for the purpose of this lecture, think of these partial symbols and dd theta 1 as exactly the same thing, and don't worry about whether there are any differences. I'm going to try to use the mathematically precise notation, but for our purposes, these two notations are really the same thing. But so let's see what this equation will do. So we're going to compute this derivative. I'm not sure if you've seen derivatives in calculus before, but what the derivative at this point does is basically saying, let's take the tangent to that point, like that straight line, that red line is just touching this function, and let's look at the slope of this red line. That's what the derivative is. It says, what's the slope of a line that is just tangent to the function? Okay, and the slope of a line, of course, is just, right, this height divided by this horizontal thing. Now, this line has a positive slope, so it has a positive derivative, and so my update to theta is going to be theta 1 gets updated as theta 1 minus alpha times some positive number. Okay, in alpha, the learning rate is always a positive number. And so I'm going to take theta 1 gets updated as theta 1 minus something. So I'm going to end up moving theta 1 to the left. I'm going to decrease theta 1. And we can see this is the right thing to do, because I actually want to head in this direction, to get me closer to the minimum over there. So gradient descent so far seems to be doing the right thing. Let's look at another example. So let's take my same function j. Let's try to draw the same function, j of theta 1. And now let's say I had instead initialized my parameter over there on the left. So theta 1 is here. I'm going to add that point on the surface. Now my derivative term, dd theta 1, j of theta 1, when evaluated at this point, I'm going to look at, right, the slope of that line. So this derivative term is the slope of this line. But this line is slanting down, so this line has negative slope. Right? Or alternatively, I say that this function has negative derivative, just means negative slope at that point. So this is less than or equal to 0. So when I update theta, I'm going to have theta gets updated as theta minus alpha times a negative number. And so I have theta 1 minus a negative number, which means I'm actually going to increase theta, right? Because this is minus of a negative number. It means I'm adding something to theta. And what that means is that I'm going to end up increasing theta. And so I'm going to start here and increase theta, which again seems like the thing I wanted to do to try to get me closer to the minimum. So this hopefully explains the intuition behind what the derivative term is doing. Let's next take a look at the learning rate term alpha and try to figure out what that's doing. So here's my gradient descent update rule, right? It's this equation. And let's look at what could happen if alpha is either too small or if alpha is too large. So in this first example, what happens if alpha is too small? So here's my function j of theta. Let's say I start here. If alpha is too small, then what I'm going to do is going to multiply my update by some small number. So I end up taking, it's like a baby step like that. Okay? So that's one step we're going to take. Then from this new point, I'm going to take another step, but if alpha is too small, I'm going to take another little baby step. And so if, if my learning rate is too small, I'm going to end up, taking these tiny, tiny baby steps to try to get to the minimum. And I'm going to need a lot of steps to get to the minimum. And so if alpha is too small, gradient descent can be slow because it's going to take these tiny, tiny baby steps, and so it's going to need a lot of steps before it gets anywhere close to the global minimum. Now, how about if alpha is too large? So here's my function j of theta. Turns out if alpha is too large, then gradient descent can overshoot the minimum and may even fail to converge or even diverge. So here's what I mean. Let's say I start off theta there. It's actually pretty close to minimum. So the derivative points to the right, but if alpha is too big, I'm going to take a huge step. Maybe I'll take a huge step like that. Right? So I end up taking a huge step. And now my cost function has actually gotten worse, because I start off with this value, but now my value has actually gotten worse. Now my derivative points to the left. It says I should decrease theta. But if my learning rate is too big, I may take a huge step going from here all the way out there. So I end up going out there, right? And if my learning rate is too big, I can take another huge step on the next iteration and kind of overshoot and so on until you notice I'm actually getting further and further away from the minimum. And so if alpha is too large, it can fail to converge or even diverge. Now, I have another question for you. So this is a tricky one, and when I was first learning this stuff, it actually took me a long time to figure this out. What if your parameter theta1 is already at the local minimum? What do you think one step of gradient descent will do? So let's suppose you initialize theta1 at the local minimum. So suppose this is your initial value of theta1 over here, and is already at a local optimum, at a local minimum. It turns out at the local optimum, your derivative will be equal to 0. So let's look at that slope, right? There's that tangent point. So the slope of this line will be equal to 0, and thus this derivative term is equal to 0. And so in your gradient descent update, you have theta1 gets updated as theta1 minus alpha times 0. And so what this means is that if you're already at the local optimum, it leaves theta1 unchanged, because it gets updates theta1 equals theta1. So if your parameter is already at the local minimum, one step of gradient descent does absolutely nothing. It doesn't change the parameter, which is what you want, because it keeps your solution at the local optimum. This also explains why gradient descent can converge to local minimum even with the learning rate alpha fixed. Here's what I mean by that. Let's look at an example. So here's a cost function j of theta that maybe I want to minimize. And let's say I initialize my algorithm, my gradient descent algorithm, out there at that magenta point. If I take one step of gradient descent, maybe it'll take me to that point, because my derivative is pretty steep out there, right? Now I'm at this green point, and if I take another step of gradient descent, you notice that my derivative, meaning the slope, is less steep at the green point than compared to at the magenta point out there, right? Because as I approach the minimum, my derivative gets closer and closer to 0 as I approach the minimum. So after one step of gradient descent, my new derivative is a little bit smaller. So when I take another step of gradient descent, I will naturally take a somewhat smaller step from this green point than I did from the magenta point. Now I'm at a new point, the red point, and then now even closer to the global minimum. So the derivative here will be even smaller than it was at the green point. So when I take another step of gradient descent, now my derivative term is even smaller, and so the magnitude of the update to theta1 is even smaller. So take a small step like so. And as gradient descent runs, you will automatically take smaller and smaller steps until eventually you're taking very small steps, and you finally converge to the local minimum. So just to recap, in gradient descent, as we approach a local minimum, gradient descent will automatically take smaller steps. And that's because as we approach the local minimum, by definition, the local minimum is when this derivative is equal to 0. So as we approach the local minimum, this derivative term will automatically get smaller, and so gradient descent will automatically take smaller steps. So this is what gradient descent looks like, and there's so actually no need to decrease alpha over time. So that's the gradient descent algorithm, and you can use it to try to minimize any cost function j, not the cost function j that we defined for linear regression. In the next video, we're going to take the function j and set that back to be exactly linear regression's cost function, the squared cost function that we came up with earlier, and taking gradient descent and the squared cost function and putting them together that will give us our first learning algorithm. That will give us our linear regression algorithm. In previous videos, we talked about the gradient descent algorithm, and we talked about the linear regression model and the squared error cost function. In this video, we're going to put together gradient descent with our cost function, and that will give us an algorithm for linear regression, for fitting a straight line to our data. So this was what we worked out in the previous videos. There's our gradient descent algorithm, which should be familiar. And here's the linear regression model with our linear hypothesis and our squared error cost function. What we're going to do is apply gradient descent to minimize our squared error cost function. Now, in order to apply gradient descent, in order to write this piece of code, the key term we need is this derivative term over here. So you need to figure out what is this partial derivative term, and plugging in the definition of the cost function j, this turns out to be this, sum from I equals 1 through m of this squared error cost function term. And all I did here was I just plugged in the definition of the cost function there. And simplifying a little bit more, this turns out to be equal to this, sum from I equals 1 through m of theta 0 plus theta 1 xi minus yi squared. And all I did there was I took the definition for my hypothesis and plugged it in there. And turns out we need to figure out what is this partial derivative for two cases, for j equals 0 and for j equals 1. So we want to figure out what is this partial derivative for both the theta 0 case and the theta 1 case. And I'm just going to write out the answers. It turns out this first term is simplifies to 1 over m sum from over my training set of just that, xi minus yi. And for this term, partial derivative with respect to theta 1, it turns out I get this term, minus yi times xi. Okay? And computing these partial derivatives, sort of going from this equation, right, going from this equation to either of the equations down there, computing those partial derivative terms requires some multivariate calculus. If you know calculus, feel free to work through the derivations yourself and check that if you take the derivatives, you actually get the answers that I got. But if you are less familiar with calculus, don't worry about it, and it's fine to just take these equations that were worked out, and you won't need to know calculus or anything like that in order to do the homework or to implement gradient descent and get that to work. But so armed with these definitions, or armed with what we worked out to be the derivatives, which is really just the slope of the cost function j, we can now plug them back into our gradient descent algorithm. So here's gradient descent for linear regression. We're just going to repeat until convergence. Theta 0 and theta 1 get updated as this thing minus alpha times the derivative term. So this term here. So here's our linear regression algorithm. This first term here, that term is of course just the partial derivative with respect to theta 0 that we worked out on the previous slide. And this second term here, that term is just the partial derivative with respect to theta 1 that we worked out on the previous slide. And just as a quick reminder, you must, when implementing gradient descent, there's actually this detail that you should be implementing it so the update theta 0 and theta 1 simultaneously. So let's see how gradient descent works. One of the issues we saw with gradient descent is that it can be susceptible to local optima. So when I first explained gradient descent, I showed you this picture of it, going downhill on the surface, and we saw how depending on where you initialize it, you can end up at different local optima. You end up, here or here. But it turns out that the cost function for linear regression is always going to be a bowl-shaped function like this. The technical term for this is that this is called a convex function. And I'm not going to give the formal definition for what is a convex function, C-O-N-V-E-X, but informally, a convex function means a bow-shaped function, you know, kind of like a bow-shaped. And so this function doesn't have any local optima except for the one global optimum. And thus gradient descent on this type of cost function, which you get whenever you're using linear regression, it will always converge to the global optimum because there are no other local optima other than the global optimum. So now let's see this algorithm in action. As usual, here are plots of the hypothesis function and of my cost function j. And so let's say I've initialized my parameters at this value. You know, let's say usually you initialize your parameters at 0, 0, theta 0, and theta 1 equals 0. But for illustration, in this particular implementation of gradient descent, I've initialized, you know, theta 0 at about 900 and theta 1 at about minus 0.1. Okay, and so this corresponds to h of x equals, you know, minus 900 minus 0.1x is this line. And so we're out here on the cost function. Now, if we take one step of gradient descent, we end up going from this point out here, a little bit to the down and left, to that second point over there. And you notice that my line changed a little bit. And as I take another step of gradient descent, my line on the left will change, right? And I've also moved to a new point on my cost function. And as I take further steps of gradient descent, I'm going down in cost, right? So my parameters is sort of following this trajectory. And if you look on the left, this corresponds to hypotheses that, you know, seem to be getting to be better and better fits to the data until eventually I've now wound up at the global minimum, and this global minimum corresponds to this hypothesis, which gives me a good fit to the data. And so that's gradient descent, and we've just run it and gotten a good fit to my data set of housing prices, and you can now use it to predict, you know, if your friend has a house that costs of size 1250 square feet, you can now read off the value and tell them that, I don't know, maybe they can get $250,000 for their house. Finally, just to give this another name, it turns out that the algorithm that we just went over is sometimes called batch gradient descent. And it turns out in machine learning, I don't know, I feel like us machine learning people, we're not always great at giving names to our algorithms. But the term batch gradient descent means that refers to the fact that in every step of gradient descent, we're looking at all of the training examples. So in gradient descent, you know, when computing derivatives, we're computing these sums, right? This sum of. So in every step of gradient descent, we end up computing something like this that sums over all m training examples. And so the term batch gradient descent refers to the fact that we're looking at the entire batch of training examples. And again, this is really maybe not a great name, but this is what machine learning people call it. And it turns out that there are sometimes other versions of gradient descent that are not batch versions, but that instead do not look at the entire training set, but look at small subsets of the training set at a time. And we'll talk about those versions later in this course as well. But for now, using the algorithm you just learned about, or using batch gradient descent, you now know how to implement gradient descent for linear regression. So that's linear regression with gradient descent. If you've seen advanced linear algebra before, so some of you may have taken a class in advanced linear algebra, you might know that there exists a solution for numerically solving for the minimum of the cost function j without needing to use an iterative algorithm like gradient descent. Later in this course, we'll talk about that method as well, that just solves for the minimum of the cost function j without needing just multiple steps of gradient descent. That other method is called the normal equations method, but in case you've heard of that method, it turns out that gradient descent will scale better to larger data sets than that normal equation method. And now that we know about gradient descent, we'll be able to use it in lots of different contexts, and we'll use it in lots of different machine learning problems as well. So, congrats on learning about your first machine learning algorithm. We'll later have exercises in which we'll ask you to implement gradient descent and hopefully see these algorithms work for yourselves. But before that, I first want to tell you in the next set of videos, I first want to tell you about a generalization of the gradient descent algorithm that will make it much more powerful. And I guess I'll tell you about that in the next video. You now know about linear regression and gradient descent. The plan from here on out is to tell you about a couple important extensions of these ideas. Concretely, here they are. First, it turns out that in order to solve this minimization problem, turns out there's an algorithm for solving for theta 0 and theta 1 exactly without needing an iterative algorithm, without needing this algorithm like gradient descent that we had to iterate, multiple times over. So it turns out there are advantages and disadvantages of this algorithm that lets you just solve for theta 0 and theta 1, so basically just in one shot. One advantage is that there's no longer a learning rate alpha that you need to worry about and set, and so it can be much faster for some problems. We'll talk about its advantages and disadvantages later. Second, we'll also talk about algorithms for learning with a larger number of features. So far we've been learning with just one feature, the size of the hulls, and using that to predict the price. So we're trying to take X and use that to predict Y. But for other learning problems, we may have a larger number of features. So for example, let's say that you know not only the size, but also the number of bedrooms, number of floors, and the age of home of these houses, and you want to use that to predict the price of the houses. In that case, maybe we'll call these features X1, X2, X3, and X4. So now we have 4 features. We want to use these 4 features to predict Y, the price of the house. It turns out with all of these features, 4 of them in this case, it turns out that with multiple features it becomes harder to plot or to visualize the data. So for example, we try to plot this type of data set. Maybe we'll have the vertical axis be the price, and maybe we can have one axis here and another one here where this axis is the size of the house and that axis is the number of bedrooms. But this is just plotting, right? My first 2 features, size and number of bedrooms, and when we have these additional features, I don't know, I just don't know how to plot all of these data, right? Because I need like a 4-dimensional or a 5-dimensional figure. And I don't really know how to plot, something more than like a 3-dimensional figure, like what I have over here. Also, as you can tell, the notation starts to get a little more complicated, right? So rather than just having XR features, we now have X1 through X4, and we're using these subscripts to denote my 4 different features. It turns out the best notation to keep all of this straight and to understand what's going on with the data, even when we don't quite know how to plot it, it turns out that the best notation is the notation of linear algebra. Linear algebra gives us a notation and a set of things, or a set of operations that we can do with matrices and vectors. For example, here's a matrix where the columns of this matrix are, the first column is the sizes of the 4 houses, the second column was the number of bedrooms, that's the number of floors, and that was the age of the home. And so a matrix is this block of numbers that lets me take all of my data, all of my x's, all of my features, and organize them efficiently into sort of one big block of numbers like that. And here is what we call a vector in linear algebra, where the 4 numbers here are the prices of the 4 houses that we saw on the previous slide. So in the next set of videos, what I'm going to do is do a quick review of linear algebra. If you haven't seen matrices and vectors before, so if all of this, everything on this slide is brand new to you, or if you've seen linear algebra before, but it's been a while, so you aren't completely familiar with it anymore, then please watch the next set of videos, and I'll quickly review the linear algebra you need in order to implement and use the more powerful versions of linear regression. It turns out linear algebra isn't just useful for linear regression models, but these ideas of matrices and vectors will be useful for helping us to implement and actually get computationally efficient implementations for many later machine learning models as well. And as you can tell, these sorts of matrices and vectors will give us an efficient way to start to organize large amounts of data when we work with larger training sets. So in case you're not familiar with linear algebra, or in case linear algebra seems like a complicated or scary concept because we've never seen it before, don't worry about it. It turns out in order to implement machine learning algorithms, we need only the very, very basics of linear algebra, and you'll be able to very quickly pick up everything you need to know in the next few videos. Concretely, to decide if you should watch the next set of videos, here are the topics I'm going to cover. Talk about what are matrices and vectors, and talk about how to add, subtract, multiply matrices and vectors, and talk about the ideas of matrix inverses and transposes. And so if you're not sure if you should watch the next set of videos, take a look at these two things. So if you think you know how to compute this quantity, that's a matrix transpose times another matrix, if you think you know, if you've seen this stuff before, if you know how to compute the inverse of a matrix times a vector minus a number times another vector, if these two things look completely familiar to you, then you can safely skip the optional set of videos on linear algebra. But if these concepts, if you're just slightly uncertain what these blocks of numbers, what these matrices and numbers mean, then please take a look at the next set of videos, and it will very quickly teach you what you need to know about linear algebra in order to program machine learning algorithms and deal with large amounts of data.